But the nice thing, I guess, is we're now moving to a stage where we've rattled through quite a lot of different theory. We've looked at time response, we've looked at system identification, we've looked at block diagrams, we've looked at controller configurations, we've introduced ourselves to the S-plane. We've been gathering lots of different things, and we're now in the position where we're just on the verge of bringing it all together to do something useful with it, really. So a lot of the exercises from now on, if you look at the tutorial sheets and things, I was working with sort of the group this afternoon. We're all working on tutorial 6, which is here's some information about a system in the shape of a response graph. Figure out what it is, stick it in the block diagram, simplify the block diagram, design a controller. So we're pulling all these bits together now into a whole task. Okay, so we're hopefully getting towards that stage of the module, which is, I guess, with any luck, you might call consolidation. We've still got a few new things to introduce, but we'll spend more time trying to tie it all together so it makes a bit of sense. So what I want to talk about first is a bit of an extension on the frequency response stuff that we did last time. Because last time we rushed through what frequency response is and how to relate Bode plots to frequency response, and if you've got frequency response data, how to use it to work out a system model, a system transfer function. One thing I haven't talked about yet is, that's a recap, the bit at the bottom, stability and performance margins, because one thing we can use this frequency response information for is predicting closed loop behavior. If we get open loop frequency response knowledge, we can use it to predict behavior. Okay, and we'll get to that. I'm going to do a bit of revision stuff from last week first, but we'll get to that, and that's the new bit for today. So just to go through, we talked about this stuff last week. We've got a transfer function. How do we build a Bode plot? And I suggested that you should have taken that Word document from Blackboard and drawn the pictures in the little boxes and added them together. Did anybody bother? Did anybody spend some time adding pictures together? Okay. Let's do it on the board then. Okay. So what I've got there is a relatively complicated system transfer function. If you multiply out the denominator, you're going to get an S cubed, so I could describe this as being a third order sort of system. And what would its frequency response be? How would this system behave when it's subjected to sinusoidal inputs? Well, with all of these things, I've been going on about this quite a bit, so most of you are quite fed up of it. Let's make sure that we describe these things in standard forms where we can. Okay. So there's a little bit of algebra. Just taking my quadratic in here and expressing it in standard forms. And the form that I prefer, okay, because if you look, there's always two forms. The one that is 1 over 1 plus something s squared, okay, is the one that I would favour in most instances. The one that's omega n squared over omega n squared plus something, yes, handy, but I prefer 1 over 1. Yes, sir?
Is that supposed to be 2,500 on the S term at the bottom?
Where are we? Down. Which one are you looking at? Down here? That one?
No, on the bottom right, 1,500.
Oh, it is, isn't it? That's another one of my classic typos. Sorry about that. Okay, so this is just linear algebra, sorting things out badly into a standard form. Okay, that should indeed be 2,500. So what I've ended up with is a gain of 0.1. Okay. There's a differentiator in there, isn't there? It's an S term by itself. There's a first order lag with a corner frequency of 5 radians per second, and the second order lag with a corner frequency of square root 2,500, which is 50 radians per second. So by putting things into the standard form, it's quite easy then to identify what we've got. And then, from that list on that Word document, I can look up, well, what do the Bode plots in amplitude and phase look like for those building blocks? Okay, this is a gain of 0.1. Convert that to decibels, 20 times the log to the base 10 of 0.1, and we just get minus 20 dB. Gains, you know, don't contribute any phase shift, so that's just flat line. There's my differentiator. It's got an upward slope of 20 decibels per decade, and it always contributes plus 90 degrees of phase shift. There's our first order lag with a corner frequency of 5 radians per second and a minus 20, and you can see that the phase shift starts off at 0, ends up at minus 90. And here is the second order lag, corner frequency of 50, change in slope of minus 40 decibels per decade. And again, looking at the phase plot, starts off with nothing, ends up at minus 180, and is halfway through that change at 50 radians per second. Okay. We can pull all this off the shopping list on that document. What I didn't go through with you in the lab, or in the lecture I should say, sorry, is I think I very glibly said you now need to add those pictures together. Okay. Because these are logarithmic, we need to add these up, has the same effect as multiplication. So how do we do that? Well, it's actually much more simple than it first seems. You do literally add up the numbers. So if I take these first two, okay, this has got an upward slope of 20 decibels per decade. This is just a constant value of minus 20. So if you add those together, what's going to happen is they're going to get a resultant which is a line equal gradient but 20 decibels below this one. 0 plus 90 is plus 90. So it should do that. Okay. And this is exactly how you add pictures together. So I've now got this line with a plus 20 gradient, and I need to add my first order lag to it. Well, up until the corner frequency nothing happens because that lag term is 0. Once I get to 5 radians per second, I'm contributing a downslope of minus 20 decibels per decade. So what do you think happens when I add a plus 20 decibel per decade slope to a minus 20 decibel per decade slope? Yeah, absolutely. You can't see the hand signals. We're getting this with the biro, which is exactly right. It cancels out, doesn't it? And we also add in this phase change, and we get that. Same process again for the second order one. Nothing at all happens to the amplitude until we get to the corner frequency. After that it's minus 40, so we end up doing that. Okay, so adding these pictures is actually quite easy. It's a bit alien, it's not a thing that we do on a daily basis, but adding pictures is not complicated. It's corrected itself, I notice. Okay. So generating these straight line approximation Bode plots from a transfer function is really just a procedure. It's pick the individual building blocks out of the library, draw them separately, then add them all together again. Okay. If it's something you don't like to do, it's always easier to do it on a piece of graph paper, because you can even go so far as to add the squares up to make sure that your addition is correct. Okay, so that represents the Bode amplitude plot for this system. Okay, and this represents the phase plot. I'll confess right now that the phase plot is a bit of a cheat. The trouble with these phase plots is that these phase changes take a very long time to happen. So if I go back to my shopping list one, this first order lag system here, I've kind of freehand drawn the phase changes happening. I know it's halfway through at 5 radians per second. What I haven't made clear on that, it actually takes 2 decades to happen. That phase starts to change at 0.5 radians per second and it finishes at 50 if you put a straight line approximation to it. So that's actually quite a large spread, which means this one, the second order one, oops, where's it gone? Sorry. The second order one, if it's critically damped, will also take 2 decades to happen. So this one starts at 5 and ends at 500. The end result of all that is when you get the summation of the phase plots, this is all nicely separated out. But in fact they tend to blur into one. Okay? So generating the real phase plot, if the corner frequencies are anything closer together than a factor of 100, is that they all tend to blur into one, which is why it's actually normally much easier to focus on the amplitude plot and just use the phase plot for confirmation. So that's how you add pictures together. Is that okay? Yeah. Sketch them out, add them together, you get the resultants. Let's quickly run through doing this the other way round. Hope you read the handout last week. We can use the Bode plot. I think we've done this one actually. Plot your amplitude and phase data on a Bode plot. Logarithmic axis on the frequency, logarithmic units for the amplitude, degrees for the phase, and fit straight lines to it. Take your ruler with you. And those straight lines, those asymptotes, have to be at particular slopes. Plus or minus 20, plus or minus 40, plus or minus 60 decibels per decade. And then let's use these relationships to figure out the transfer function. I think I've gone through this with you, so forgive me if it's the same one. There's a set of data, there's the graph it produces. We have done this one, I think. The red dots are the amplitude, the green dots are the phase. Let's start off with the amplitude and see. Well, I'll ask you, does that have an initial slope, do you reckon? Or does the data start off level? If you were to draw a pencil line through that, best fit line through the red dots, does it start off with a gradient or does it start off level? It's got a gradient, hasn't it? Is it an... I can see you yawning because you've obviously had a tough week. Does it go uphill or downhill? Down. So I've got a negative gradient. What sort of things will give me a negative gradient right from the very, very beginning? No, what part of a transfer function always gives me a negative slope right from the left hand side? An integrator. It's the only thing that does that. Okay. So I reckon this system involves an integrator. So I'm going to try and fit a straight line to ascertain the angle. Minus 40 is too steep, so let's go back to minus 20. Minus 20 decibels per decade, which ties in with this idea there's an integrator involved. Okay, what else is going on? Well, there's a change in slope because this lot don't fit my minus 20 line anymore, so I'm going to try and fit it backwards starting at the other end. Closest I can manage is minus 60. Okay. You just do this with your ruler. It's ever so easy. And what we find is we've got evidence of an integrator. If it was an integrator by itself, at what frequency would it pass through 0 dB?
1 radian per second.
1 radian per second. So, is this an integrator by itself? Yes or no? No, because it doesn't pass through 0 dB. If it did, it'd be over here somewhere, wouldn't it? So something has lifted that up. What can I put in there that just lifts the whole line upwards by a constant value? A gain. So I've got a gain, an integrator, and then I start looking for corners, and my slope around this corner changes from minus 20 to minus 60, so that's a change of minus 40 decibels. What gives me a change of minus 40 decibels as we go around the corner?
Second order lag.
Second order lag. And then the rest of the plot with the data that I have just carries on in a straight line, so I'm finished. I've got a gain, the value of which I can work out by extrapolating that or just by looking at where we are relative to 0 dB. There's an integrator term and there's a second order lag. And the second order lag has an omega n value of something like 19 radians per second. Okay, 20. The dotted line is the real data, the straight lines are my asymptotes. How we tell or how we estimate zeta is based on the difference between the asymptotes and the real data at the corner. Okay. If that difference is large and negative, so the real data is beneath, then that's got lots and lots of damping in it, that's a large zeta. If the real data goes above the corner, that's got not very much damping at all, it's exhibiting a resonant peak. So that's a small zeta. The magic number for a second order system is if it's critically damped, the difference between the asymptotes and the real data is minus 6 decibels. Okay, and that indicates critical damping. Oops, excuse me. Okay, let's have a quick look at the phase. Phase data is notoriously less reliable, it's much harder to measure. We're starting off at minus 120 degrees or so, minus 110, something like that, which is sort of consistent with having an integrator. An integrator would put us at minus 90, but we're already feeling the effects of this corner because it's only about a decade away. Okay, and we get a change all the way down towards and probably past minus 260 towards minus 270, which is minus 90 from the integrator and another minus 180 because of the second order lag. You know all that. Let's hop through this. There's a bit on that slide about working out K. Make sure you check that one out. There it is. Okay, 5 over S times 1 plus, and in our case we can actually estimate zeta as 1 because we had minus 6 dB. Okay. So just very quickly we've gone through the idea of transfer function to Bode plot, and now we've gone Bode plot back to transfer function. Okay, so we use straight line approximations to do this. That's only possible because we use logarithmic values. I just chucked a few examples in just to prove it. These are MATLAB plots. Okay, so those of you that like to drive MATLAB might wish to play with this, and surprise, surprise, the command in MATLAB is simply BODE, B-O-D-E. Okay, so if you set up a transfer function, numerator is 2, denominator is 0.1, comma 1, which is the coefficients of S in descending order, then just press bold and it'll give you these pictures. Starts off level, so there's no integrators, no differentiators. It doesn't start off at 0 dB, so there is a gain. And there's a corner around here somewhere, which is, can't even read it myself, but hopefully something like 10 to the 1. Okay. Oh, there it goes, in fact. Okay, so there's a corner at 10 to the 1, and we're also halfway through the phase change at that point. Being first order, we don't have an option for different zetas. The real data for a first order one is always 3 decibels beneath the intersection of the asymptotes. There's a second order one. What I've done in this one is I've introduced 3 different zeta values so you can see the difference. Okay. Zeta equals 1 is the blue one in the middle. Okay, and if I put my asymptotes in just a second, you'll see that's a 6 dB drop. Large zeta, you get a much bigger difference in here. Zeta equals 10 gives us the red one, and zeta 0.1, we get this resonant peak on the data. You can see when we apply the straight line asymptotes, they're the same for all of those values. That's why if all we've got is the straight lines, we can't really tell what zeta is. Let's have a look at what's happening to the phase. Okay. Zeta equals 1, the blue one in the middle. You can see it takes roughly, well, if you say from there to there is 2 decades. It takes roughly 2 decades to go through that transition. The red one, which is the high damping ratio zeta, takes ages, and it's almost showing up as 2 separate events, isn't it? The low damping one, the phase changes over very quickly. So again, you can get some information about what's going on. Right, here's the quiz. When does a second order system with lots of damping split into 2 first order systems? Because mathematically they're the same. Yeah. If you take that quadratic and there's lots of damping in it, you can factorize it into 2 real roots. So mathematically there's no difference between 2 first order corners, one following the other, and a high damping second order system. So just be aware of that. When you draw these things, you could legitimately interpret it as 2 first order corners or 1 second order corner with lots of damping.